In this video, we're going to introduce an application of integration, computing the average value of a function. To motivate this, imagine we're looking at a greenhouse where they're tracking the level of carbon dioxide in the air. Over time, so this is day by day, there's a tracker that records the carbon dioxide level because it has an impact on plant growth. Initially, at time 0, the carbon dioxide level is 350 parts per million. That's what the ppm stands for. And then it goes up, and then it goes up further, and ends up resting around 450 over this week. One thing that might be of interest to someone managing the greenhouse is the average level of carbon dioxide over that period, as a summary statistic. Looking at the graph, it seems that a bunch of time is spent down here below 400, around 350, 375, and then also a lot of time is spent in the 425 to 460 range. Well, what would our intellectual or first guess at the average be? Maybe somewhere around the 400 level, maybe a little bit above. That seems like a reasonable estimate for an average. What that is telling us is that we already have an intuition for what we mean by an average based on a graph. What we're going to do next is try to solidify that understanding and develop a formula that will let us compute the exact value of the average given a graph like this, or a formula for the function. It will help us if we can look at units for this. In the last statement, we said the average value would be around 400, and the units implied there would be parts per million. So the key thing here is that the average has the same units as the y-axis on the graph. That's going to help us tease our way through to a formula for the average. Let's do that in a little more abstract way. We're going to look at the function y equals x squared on the interval from -2 to 2. If we draw that parabola, it would look like this. Here there aren't any units to guide us, but we have values that are ranging from 4 down to 0. And again, the values are 4 at the max, 0 at the lowest, somewhere in the middle here. Maybe there. That sounds not unreasonable. But we really need to focus on what we're looking for. Let's go to the next page. If we have an average value for a function, what makes it the average value? There are a number of ways to define this, but the most common one is to look at, let's imagine something too high. If we drew this as our average value, and then let's say something that's just about right, and then something that's way too low. So this is too high. This is too low. If this is our average, let's call it A here. And this one here is around right. What makes that match our intuition? Well, knowing that we're connecting this to integration, one of the ways to define this is areas. If this was our average value, notice how little area there is above the line that we drew compared to the area below down here. There's an imbalance. This average is not average because less of the graph is above and more of the graph is below this line that we drew. In contrast, if we pick an average that's too low and we sketch out the areas above and below, then here we see that there's too much area above relative to this average line and less area below. The sweet spot looks like it actually might be a bit lower than this. Let's draw that one more time. Let's say around there. This area seems nicely balanced with this area here. Maybe even a little lower than what I drew there to make those green areas equal or counterbalance the area in red. Well, what does that give us in terms of an insight for a formula? What is the difference in those areas? Well, one way to look at it is each of these little rectangles that we draw building our integral would involve the difference of f of x minus the value a, minus our average value a. And what are we doing as we compute this relative integral here? We're adding up the f of x minus a values times little bits of width, and we're contributing the green areas here as positive contributors, the red areas as negative contributions, and that's actually done by this formula here. If f of x gets below a, this red region, then this whole thing would be negative. When f of x is higher, we get positive values, and so this is exactly what we want in terms of the formula, and if those are perfectly balanced, we're going to get an integral that equals 0. As we add up the function minus a, we're going to get positive things for these green regions, negative contributions for this red region, and if we want them perfectly balanced, the integral will work out to exactly 0. So that's a fun way to already connect the idea of an average value, which is just a vertical level, with the idea of integration. However, this makes it challenging to actually get the value of the average we want. So notice that we have this, we know what f of x is, but what we want is this average value a. So what we're going to try to do here is solve for a. This is a little tricky just because of the integral part, but there's only one gotcha step. Because we have a difference here, it's not a product, we can simply integrate the f of x part, and then we can integrate the a part. And then we can focus in on this region here. If we do a little side calculation, the integral of a with respect to x, a is not an x value, a is a constant. So we anti-differentiate a constant, we get a times x on the interval from b to a, and then we plug that b value in for x, we plug that a value in for x, we end up with a times b minus a. So our average value times the interval width. That's what b minus a always represents. In this case here, it'd be the whole span from a to b. How far is that distance? If you take this a, b minus a part and replace it with this expression here, we can very easily get to the formula on the next page. I'll just summarize this here first. If we isolate for a, let's turn the page and see what we get. We get a is equal to the 1 over b minus a, we bring it down, times the integral of the function f of x. Now this has a lovely area interpretation as well, or integral interpretation as well. It's most easily seen if we bring the b minus a back up onto this side though. So in this case, there are going to be two interpretations. One is the one that the average value and the function have same areas above and below, or canceling areas above and below. This new version, which is equivalent, is that we have our graph, f of x, and we compute the integral of that function, and we get an area. So this is an area under the graph if everything's positive. If I take a look at this formula here, b minus a is a width. We talked about the average value being a y value with all those units. That would be a height, which is better known, combined together, as the area of a rectangle. So what is this statement saying? If I integrate my function, I get an area. The average value is the height that would make up a rectangle with exactly the same area. So a such that we have a rectangle with the same area as the integral f of x dx on that a to b span. Once we draw that, we can see that same element we talked about earlier. The part of the graph that lies above the average will be perfectly counterbalanced with the area that lies below the graph, but we can also think of it now as taking the part of the graph that's above some average and squishing it down, pushing up the other areas, basically treating the area as Play-Doh and reshaping it into some rectangle. The height that we end up with when we do that reshaping is what we're going to mean by the average value. Now we're not going to ask, now it's not likely we're going to ask for an explanation of this, but it can be tremendously helpful in memorizing formulas like this, which look incredibly abstract, to remember where it comes from. If you look on this side, this is a width times a height, that's an area, that equals an integral, which also represents an area when things are positive. So looking at it this way makes remembering this formula far, far easier. As a starting example, let's take a look at how we can apply that formula to our earlier question, what's the average value of x squared on the interval from -2 to 2? Well, the average value is going to be 1 over, what are our values for a and b? Our interval is from -2 to 2, and it's b minus a, so it'll be 2 minus minus 2. Or if you like thinking about it conceptually, it's how wide is this interval? That's an interval of 4. That's what's going to come out of this calculation. Then we also add up the total area underneath the graph from -2 to 2 of our function x squared dx. So we're going to find all of this area here. Well, what does that end up with? 1 over 4. The integral of x squared is x cubed over 3. And we're going to evaluate that at 2 and -2. We have 1/4, 2 cubed over 3 minus -2 cubed over 3. That's our fundamental theorem of calculus being applied to the antiderivative. And we have a double negative. Cubing doesn't change the signs. So we're going to have 8 plus 8 is 16 over 3. And tidying that up gives us 4/3. Or 1.33333. Let's take this back to one of our earlier graphs and confirm that that matches what we saw as a graphical intuition. In this diagram, we were trying to sketch the just right version. We can now put some scales on this. We have 0 and 1 and 2, our axis here. And so we said 1/3, which is right here. If we draw our average on that, be a little bit above that, it's 1.5 above, we can see the area here matches quite nicely. In fact, exactly, if we've done our graph correctly, matches perfectly with the area above this average line. So we have successfully identified an average, at least defined in this way, which will be the only way we define it in this course. We now also have that process formula-based for arriving at that average value, which is a very powerful tool. If it helps, there's also another way to think of this, which is thinking back to your early version of averages, which was find the total amount. In other words, take a sum of all the numbers you're working with, and then divide by the number of values that you're averaging. We have the same feel in this formula here. Add up the whole area under the graph, and then divide by how much X distance you had to cover to get that. So it has the same feel as the more traditional sum of numbers averages that we will have seen before. Lots of connections, both to integrals and to earlier intuitions.